Okay, hello, and in this video I'm going to share a package I got. This package here that looks like any other package is not from 2020, it's from around 1950. And you see, when we open it up, there's packing pellets. Let me dig inside, see what we can get here. Been meaning to take more of these out. Haven't gotten around to it yet. Aha! Little cartons of boxes here. We got the right one. Here we go. As you can see, set the box down. Inside is a little, almost like the box they would use for a Matchbox car. And it says 10 EG7, and you can open the box, and inside, very old packaging, half a century at least, is a vacuum tube, the same ones I showed in my last video. I'm going to try to build an arithmetic unit out of tubes for a computer eventually, and I ordered them already so we can have them. And you can see it has the getter and the pins. Also, I've bought pin sockets, but these used to be at every drugstore, and you would buy replacement ones for your TV sets and radios. Anyways, let's put it back. It's rather fragile. You can see how, ooh, fell apart. It had the label in the front. So these used to run the world, actually. Let's learn a little bit about these amazing devices. It's not taught anymore, so the theory you're learning here is only available in period books and in videos like this. Vacuum tube theory, introduction. Now, it is known that the plate current, and the plate is the thing that picks up the electrons that are thrown off by this cathode, and there's a heating element below, not shown, follows a known linear relationship very, very closely, although there is some slight deviance towards the extremes. The plate current is the plate voltage plus mu times the grid voltage, which is negative, so this would be a negative number here, all divided by R plate. Now a typical value of R plate would be 7,000 ohms. A typical value of mu would be around 20, although it varies between 2 and about 100. For a triode, and this is the simple 3-element triode. So let's figure out how can we use this to amplify. The whole point is to amplify, to generate a larger signal in magnitude that's a replica of the input signal with fidelity. And this relationship here is what is used to do this. So we also need another relationship. We can call this EQ1. Another one we're going to call EQ2. And what does EQ2 tell us is that the plate voltage is the supply voltage, and this is V supply, this rail, less the plate current across a bias plate resistance. Don't confuse R with RP. RP is the inherent resistance to this tube, and R is the one that's external going to the rail. Two different things. And this right here is just a statement of Kirchhoff's voltage law. So you lose voltage across the resistance, that's Ohm's law here, and V supply is your high potential. So these are very fundamental. So what we can do is we can actually solve for the bias point. How this is done in this basic amplifier is you put VG on this battery here. When there is no signal, if we shorted this out or left it open, this would have a low impedance, and the voltage would appear across this on the grid, negative. So VG would turn down the plate current, which is the whole idea of biasing. It has to be negative on the grid, or the grid will suck up the current and it'll mess up the circuit. It won't amplify. It'll effectively act like a three-way short, maybe. So what we can do is we can substitute V plate from this equation into this one. And we did so here on this line. And what you would then do is multiply our plate across, so we get our plate, I plate. And from there, you get V supply minus I plate R, which is this term we just substituted, plus UVG. Our goal is to solve for I plate, which is the quiescent or bias plate current. So what we can do is we can move this term over to this side of the equation, which is done in this step here. So you add plus IR, IPR to both sides. And that would cancel this, and it would render this line here. And obviously, by division of this term here over to here, so R plate plus, of course, R, by doing this, we get the rule for the bias point of a triode amplifier, where, of course, this is the voltage of that battery, negative, which is what we use to set the bias. Mu is the constant, and our plate is the constant, and these are on the data sheets. And V supply would be your plus rail, this voltage with respect to ground, typically around 150 to 200, sometimes higher, a little bit lower for other things. So the plate current and this bias, which I call grid voltage bias, and this is a common cathode amplifier because the input and the output are common to the cathode, as you can see with the grounds. The plate current equals the supply voltage plus mu times Vg, all divided by R plate plus R. This rule is very important, and it's very easy to derive. The derivation is given right here. And from here, we know the plate current. And using EQ2, we can figure out the plate voltage. And then we can know exactly the bias point. The bias point here would obviously be I plate, V plate, and you might want to know V grid. And by quiescent, I mean at no signal. So it's implicit this is taken with 0 volts as input. And of course, the 0 volts would be the alternating current potential itself. Anyways, how this thing works, this fig 1, is you would have your transformer here and your potential input here, which would then move magnetically from primary to secondary, which is this side. It would have the negative voltage added to it. It would appear at the grid. And then based on this equation here, it would be multiplied by mu and divided by these terms. And that would appear as a current running this way. And this resistor, big R, would turn that back into a voltage. And then that voltage would be put across a larger resistance here. And so a little signal here would appear as a big signal out here. And on the next slide, I will explain exactly how the voltage gain can be determined. But hint, hint, it uses this rule here, and basically what I just stated. But it's worth noting that the grid has practically an infinite input impedance. So, I mean, it's as long as you keep the grid negative, it just behaves like an open circuit at this point, which is a major advantage of tubes, whereas the transistor, the base, behaves like a resistor. It does draw current, but in a vacuum tube, the grid just has an electrostatic potential on it, which controls the flow, because the electrons are moving in this direction, being sucked towards the plate, much like force fields you'd see in Star Trek. It happens in real life in a vacuum on a small scale. And when the grid turns negative, it repels them back, like this. But if the grid ever were to become positive, it would just suck them up, and it would show a large current. We can't have that, so the grid must always be 0 with respect to the cathode, or negative. And as you can see, the minus would be here, the plus would be here. Whenever you see a battery symbol, the littler lead is always the minus and the bigger one is always the plus. In practice, this potential would be probably 1 to 3 volts DC. But I've seen larger, and I've never seen zero bias except in a Class B amplifier. But this is a Class A amplifier, which conducts in the whole cycle of the input signal. Class B is more complicated. But this is your basic common cathode voltage amplifier, and you can also use it as a current amplifier. And I'm going to explain in the final part of this series how this fundamental theory can be used to make a simple operational amplifier out of vacuum tubes and some fundamental components. So let's move on to computing the voltage gain. I've already given you the input impedance, which is basically infinite, and the output impedance would be dominated by this resistance. Typically this is on the order of 10 to 100 kilo ohms or thereabouts, but there's exceptions with high mu and low mu tubes. Low mu would use a tinier one, high mu larger. And then you have a capacitor, not filter network, but a connection network to a larger resistance here. So your output resistance would be dominated by R, and R plate would also factor in potentially. So you know the input and output impedance, which is important for impedance matching, which I'll cover in another video. But in effect, all that's left is the voltage gain and the power gain, and that's a pretty major calculation. But it uses these values here and the equation here, namely this guy. And I will show, I have shown in a paper before, how this equation is actually followed pretty well. It seems very simple, but it does actually work. In addition, mu and R plate come off the data sheet. For instance, there's a rule, since mu is volts per volt and R plate is a resistance, sometimes they write this equation in terms of other variables. For instance, there's something you might see that's called GM, which is the plate transconductance, but GM is actually equal to mu over RP. So if you see an older data sheet, if it gives you any of the two, you can find the third, but that's a more pedantic note. We'll save that for later. But yes, let's see the voltage gain. So give me a second to rewrite this board to show you that. And I've rewritten the board. Let's find the voltage gain of a common cathode vacuum tube amplifier using a triode or 3-element tube. Well, we start with the rule we developed back here. I plate after bias, V supply plus mu VG divided by R plate plus R. And I showed the derivation of that on the last slide. So bring that rule up here, like so. And our goal is to find delta IP, which is a change in the current. Now supply voltage is fixed, that's not changing, so we can scratch him out. This term here is fixed, but is necessary because this one here is changing, VG, which is our input. And so we find the plate current change for a given grid voltage change. So you could divide that over here to get a derivative, but more on that later. What we do then is we know by EQ2 from the last slide, V supply minus I plate times R up there equals voltage plate. And we want, our goal is to get delta VP. And then we can substitute this into here, which is done in this line here. So we would have mu delta VG, correct, divided by R plate plus R, all times R, which is the external resistance up here. And then that would give us delta V. Of course, the minus sign carries down. What we can then do is divide by delta V grid, which is the input change, and we find the output change for an input change, and that is the voltage gain. So essentially we use the equation we have derived, we use one of the initial equations, so you multiply the current by R to get the equivalent voltage change, and that gives delta V plate, which would be here, delta V plate, and delta V grid would be here, delta V in, it's the same thing. And we come across the voltage gain, plug this into this, which comes from the Kirchhoff's voltage rule, voltage law equation from last time. I believe I called it EQ2. And plug this into that, and then divide the input change to get the ratio, and this is your voltage gain. So for typical values for a 6J5 here, which is a very common tube, one amplifier has a voltage, the supply voltage cancels out, but it has a mu of 20, it has an inherent plate resistance on the data sheet of 7,000, and R I set to 30,000 based on the bias concerns, and since it's being divided by here and multiplied by here and big R dominates, the voltage gain is approximately mu, which is 20, a little under. So you can easily see how mu is the maximum possible voltage gain for a triode, in effect. But what's interesting here is you have R plate plus R, the denominator, mu, and Vg is factored down here, multiply, let me divide and divide. The ratio delta V plate, change in the plate voltage, delta change in the grid voltage is your voltage gain. So it is predictable, and it can be found using our bias equation here and some common sense. No calculus required, just the change, which is delta, initial minus final, or final minus initial. That's what that means. The triangle, in case you didn't know, a delta V grid is, of course, the voltage at the grid final minus whatever value it began, the grid initial. This is a known rule. Anyways, I'll cover an actual design here shortly.